Okay, so here's the agenda of my presentation. I'll start with a brief introduction of cooperative grid arrays, which will emerge throughout the rest of the presentation. Then I'll present three topics that are connected by a common theme of concurrent memory accesses, copies, and synchronization. And finally, I'll conclude my presentation with two orthogonal topics. One is hardware-based compressible memory, which can help increase effective global memory bandwidth. And the last one is CUDA graphs, which help eliminate kernel launch overheads. First, let me say a few words on the terminology. In this talk, I'll use interchangeably CTA abbreviation, which is a synonym for a thread block, and CJ abbreviation, which is a synonym for a thread block cluster. Also, in the code snippets, I'll abbreviate namespace cooperative groups by a commonly used abbreviation CG. Okay, let's start with the first topic. And this slide is an advertisement in a sense that it advertises the main benefit of thread block clusters, which is the size of the shared memory accessible within a cluster. So square sizes here match the numbers, and as you can see, the shared memory increases roughly proportionally until we get into a Hopper CJ scenario in which total accessible size can reach up to 3.6 gigabytes. So clusters introduce another level of hierarchy, allowing to group multiple CTAs. CUDA guarantees cluster size up to 8, and this number can be higher for particular GPUs. For example, for all current Hopper cards, it allows up to 16 CTAs per cluster. Similarly to blocks and grids, CTA in a cluster can be logically organized into three-dimensional layouts, and each CTA can query its linear or, let me create a laser pointer here, can query its linear or three-dimensional rank within the cluster. So execution of the CTAs in a cluster is co-scheduled, and all the threads within the CJ can be synchronized similarly to CTA synchronization. One note on the resource utilization. For cluster sizes more than 2, it's possible that not all the DSMs will be used by a kernel. Okay, now let's talk about the advertised shared memory. Within a cluster, it forms a so-called distributed shared memory, which is accessible by all the CTAs. And in particular, threads within a CJ can read, write, or perform atomics on the distributed shared memory. They can also asynchronously copy into distributed shared memory, which will be covered separately in my presentation later. And another note on performance, distributed shared memory is not as performant as local shared memory, especially when it comes to bandwidth. So in order to access shared memory, you need to use the cooperative groups API. So here, this example shows how to map shared memory from a neighbor rank, which is denoted by a rank input variable here. And a very important note on accessing distributed shared memory is that CJ needs to be synchronized before accessing remote shared memory, because CTA co-scheduling within the CJ does not imply synchronous start. So it's possible that one CTA can try to access remote shared memory before another CTA kicks in. And for the same reason, you typically want to synchronize your kernel on exit. Okay, here I'm showing two ways to launch CJs. So you can either specify CJ size at the compile time or at the runtime. Compile time is the simplest. You just add a cluster dims attribute. For the runtime, runtime requires a bit more effort and is done with the kernel launch API that is shown here. Note that in both cases, your cluster size must divide your grid size, otherwise your kernel launch will fail. Okay, that concludes the CJ part, which was pretty short. Now I'm going to talk about the memory model. So it's not very obvious what should happen when multiple threads read and write same memory concurrently. And the purpose of the memory model, also called memory consistency model, is to define this behavior in a rigorous and formal way. However, being formal and rigorous, it makes it quite difficult to understand. So my goal today is to explain the memory model in simple terms, while at the same time providing a deep enough picture for writing correct and optimal CUDA code. OK, let's take a look at this code. Here, thread 0 writes data and then sets a flag to signal thread 1 that the data is ready. Despite reading the data after the flag here, the assertion may fail. And this behavior is explained by the weak memory model employed by CUDA, which says that writes by one thread may not be observed in the same order by the other threads. Moreover, this code is just wrong, because in CUDA, concurrent read and write of the same memory is a conflict. And here we have concurrent write of flag and read of flag. And CUDA expects that the programmer provides a conflict-free code, otherwise essentially all bets are off. So what does it take to synchronize memory accesses? Synchronization memory means taking care of these two items. I just talked about the first one, happens before relation, but also we need memory accesses to propagate to a desired level. If you don't do it, then this situation is possible. As you can see, the second SM will never see the updated value of the flag. This picture is not exactly accurate because the compiler will likely optimize out the while loop. However, it explains the idea of reaching correct point of coherency. OK, now let's take a look at some synchronization examples. The simplest and common one example is here when we write data to the shared memory, and then we read data in a different order. And we need to to insert a synchronization sync threads command in between in order to synchronize writes and read. Now, by definition, sync threads make all prior writes visible to all threads in the block, so both requirements 1 and 2 here are satisfied. A bit less common communication pattern is when we do the same with global memory. All threads write to global memory, and then they read from global memory in a different order. Again, sync threads applies to the entire memory hierarchy. So this code works as well, but it only works within the block scope. If you want to get outside of the block scope, we need to synchronize at the grid level. And again, barrier, it's a barrier plus makes all writes visible to all threads within a grid. And that holds true for both shared and global memory. So let's discuss what exactly it means to achieve second item to reach a correct point of coherency here in all these examples. So here's the slightly simplified picture of the hardware architecture. And as you can see, for thread block level access, there are no extra caches between above L1 and no incoherent caches. So this situation is pretty simple. However, for grid level synchronization, we need to reach L2, and moreover, we need to make sure that the threads do not read from the incoherent L1 caches. And this gets more and more complicated as you go deeper in the hierarchy when you go to a device or system level. Fortunately, you don't need to think about this hardware picture. So OK, let me say a few words what happens here. So as you saw before, we need to memory fence plus barrier, plus we need to invalidate all L1 caches. So fortunately, you don't need to think about this hardware picture because CUDA provides us with a scope abstraction, and all we need to think about is at what level we want to synchronize, either thread level, block, cluster, device, or system. OK, now let's talk about how we can fix the producer-consumer example. So you already saw this code. Both items are not satisfied, so the code does not work. Memory fences can enforce condition 1. However, they do not ensure that memory operations are visible to other threads. So next step to fix this code is to insert a volatile flag, which has been done traditionally. And it makes this code work in practice because volatile enforces reaching correct point of coherency. However, volatile is not a part of the memory model, and it has nothing to do with synchronization. So in particular, it does not enforce memory ordering, so we still have to keep thread fences here. But most importantly, it is not atomic, so we still have a memory conflict. We write flag here, and we read flag here. So from the standard point of view, this is still an undefined behavior. So to fix this issue, we can use atomic operations, and finally here we arrive at the correct code. These atomics do not enforce memory ordering, so we still have to keep fences. And another issue with this code is that we cannot synchronize with the CPU side because there are no compatible CPU atomics. So we can now utilize, we can finally utilize a CUDA atomic, which is an extension of the STD atomic. It makes this code elegant C++, solves the CPU communication problem. Note that explicit memory fences are gone because by default STD and CUDA atomics have a built-in memory fence. However, this code can still be made more performant. And the reason for that is that default memory ordering of STD atomics is sequentially consistent, which is essentially a very strong ordering, and because of that, very expensive. So in actuality, we don't need a total ordering. All we need to achieve is for the producer to make sure that data store does not move down past the flag store, and then data load does not move above the flag load. Plus, we need to satisfy point of coherency condition. The STD atomics provides us with fine-grained orderings that are exactly what we need, acquire and release. So for acquire, no reads or writes can be moved before acquire, and for the release, the opposite. It also ensures memory operations visibility, which means that we reach correct point of coherency. So here, finally, you see our final code, which is correct, elegant C++ code, and also efficient. Okay, lastly, I want to mention cumulativity property here, which allows us to essentially propagate synchronization. Here, thread 1 produces data and synchronizes with thread 2 that lives on the same device. Because of that, we can use thread scope device atomic. And then thread 2, it behaves as a consumer with respect to thread 1 and as a producer with respect to thread 3, where thread 3 lives on a different device. So we need a system scope atomic to synchronize with thread 3. And after this chain of synchronization, the data on thread 3 will be visible as expected. So this assert will hold true. Okay, done with the first topic. With the second topic, now let's talk about asynchronous barriers. When we synchronize, for example, with sync threads as here, threads that arrive at the sync threads line will wait to proceed until all the threads arrive here. And therefore, threads that arrive first cannot do any work. So asynchronous barriers allow us to split arrive and wait functionality and allow the threads to do some independent work in between. Memory ordering with barriers is done with respect to memory accesses before arrive and after wait, but not with respect to memory operations in between. Okay, now let's look into the barrier anatomy. So barriers track expected arrival count and optional memory transaction count, which I'll explain later. Barrier state has two main variables, current arrival count and the binary phase. And I already mentioned two main methods, arrive and wait. So first, let's talk about initialization. On initialization, both expected arrival count and current arrival count are initialized to the same user-provided value. and phase is initialized to 0. Transaction count can be incremented separately by a user, and it's automatically decremented by hardware on completion on memory transactions, which allows us to synchronize async copies, as you'll see in the next item of my presentation. Okay, now let's talk about arrive and wait methods. Arrive operation consists of 2 steps, which are, however, executed in one non-blocking atomic, as a one non-blocking atomic operation. So first, arrival count is reduced, typically by 1, but optionally you can give it another count. When it reaches 0, the phase is flipped, and the current arrival count is reset back to the expected arrival count, which allows us for barrier reusability. Note then, when transaction count is involved, this only happens after transaction count reaches 0. Wait is simply a wait for a phase flip, and there are 2 ways to wait. One way is token-based, when your arrive method creates a token, and you can pass that token to the wait. In another method, you can track phase explicitly, so you have to have a current phase, and you can wait for your barrier phase to become not equal to the current phase, and in that case, you need to flip your current phase explicitly, let's say when you are doing reusing your barrier. Okay, so before I introduce scopes in the memory model part, and this table summarizes barriers with respect to different scopes. The most interesting two are block and cluster barriers, because they are hardware accelerated on Hopper when placed in shared memory. And here I want you to note some restrictions on the barrier operations. So for cluster scope barriers, each barrier can be looked at as a local barrier, which means that it's located in a local shared memory owned by a CTA, or after you map it from a neighbor, it can be looked at as a remote barrier. So initialization and wait is not allowed on remote barriers. You can only initialize and wait on a local barrier. At the same time, you can arrive on both local and remote. When it comes to system scope, everything is allowed. You just need to make sure that your barrier is accessible by all the actors. For instance, if you're synchronizing several GPUs, you want to make sure that peer access is enabled. Okay, here's a note on the performance. So I have a typical producer-consumer pattern when there is an external loop. Producer produces data for consumer, then notifies consumer that data is ready via data barrier. And then to proceed with the next iteration, it waits for another barrier from consumer to make sure that the data is not overwritten. And consumer at the same time waits on the data barrier, then it can use produce data, and once it's done using produce data, it arrives on a copy barrier to let producer know that we can iterate again. So in case of when producer is on one GPU and consumer is on another GPU, and here I'm showing results for the Grace Hopper system, the recommendation is for placing barriers is to place them where we wait. However, in case of CPU-GPU communication, in this case, we have a large disbalance between number of CPU threads, which was in this test, I believe, 72, and number of GPU threads, which was hundreds of thousands. In this case, the recommendation is to place your barrier where the majority of the threads live. Obviously, these recommendations can change if your ratio of threads between consumer and producer is different. Okay. Now let's switch gears and talk about asynchronous data copies with respect to shared memory. So first, I'll start with dissecting standard synchronous copies. So here's a typical example when we copy data from global memory to a shared memory. And what happens under the hood is that the data travels from global memory through the cache hierarchy into a register. And then the second step is that it gets copied from a register into shared memory. So this results in a lone scoreboard stall, which you may see being reported by the NCU, which means that the second operation cannot start until the first copy is complete. On top of that, under the hood, we are wasting registers and L1 bandwidth. Similar picture is when we copy from shared memory to shared memory. Data copies through the register again, and we observe a short scoreboard stall in the NCU profile, for example. Okay, let's now take a look at this typical computational pattern. So we have a loop, which can be either time iterative loop or space loop. We first copy data into shared memory. Then we need to synchronize to make sure that shared memory is visible to everyone. Then we do our computation using shared memory, and then we synchronize again to make sure that next iteration does not overlap the shared memory while it's used by the previous iteration. So as you can see in this picture, the load and compute stages are essentially sequenced. So this does not allow us to increase bytes in flight, which we would like to achieve. So essentially, the asynchronous copy benefits allow us to have this pattern when we can copy data, say prefetch data for the next iteration while computing the current iteration. So this means that we increase bytes in flight. In addition, it allows us to bypass registers and other benefits which I will describe later. Okay, so first I'll start with a summary of asynchronous copies that are currently available. So the first one was introduced by Ampere architecture, and it allows only one direction of the copy, from global memory to shared memory. It's essentially a synchronous version of the assignment operator. And then, since we are doing copies asynchronously, we need to introduce some tool to synchronize the operations on completion. So synchronization column here lists how the asynchronous copies can be synchronized. Then some examples of C++ code to invoke those operations, and finally SAS operations that these copies get mapped into. Hopper introduced a bunch of other copies, and now I'm going to talk about each of these operations separately. So let's start with Ampere. So let's first take a look at the picture on the right. As you can see, the data travels from global memory and L2 cache directly into shared memory by passing registers. If the size and alignment of your copy type is 16-byte, then it follows this red path, so it goes directly into shared memory, bypassing L1 as well. However, for two other allowed sizes, which are 4 and 8 bytes, it first goes into L1 cache and then into shared memory. Okay, so let's talk about how to code it. So there are 3 operations that we need to do. First one, pipeline memcopy async actually fires the asynchronous copy. And we can fire several of them, after which we need to attach our synchronization barrier to the previously fired instructions. So that's what pipeline commit does, and it introduces a batch counting barrier for a group of copies fired between 2 consecutive commits. So after we have multiple commits, multiple batches committed, we can wait on the completion of all of them except last n by using this function call. So let me show what it means. So here I fire first batch, second batch, and third batch, and I wait for all the batches except last 2, which means I wait for this green stuff to complete. If I wait with the argument 0, it means that I wait for all previously fired asynchronous copies. Okay, one note with respect to this. So pipeline commit always behaves as a full warp level instruction. So if we commit in divergent code, the number of previous commits equals to the number of divergent branches, which can be runtime dependent. So let's take a look at this code. First we do an unconditional commit, and then we have another commit under if and else branches. And here we intend to wait for the first one. However, we may end up overweighting in the case of divergence because in reality, we're going to wait for either unconditional commit and if commit or unconditional commit and else commit. So this does not break the code. However, it makes it less performant. So the recommendation here is do not commit in divergent code. OK, now let's take a look at a particular use case. So this is typical for, say, finite difference simulations when we load data into shared memory, including some halos to cover stencils. And in this particular example, one peculiarity here is that I load into shared memory from different global memory arrays. So from the left one here, from the central, and from the right one here. This may happen when, for instance, you have a multi-physics simulation and you are stitching physics domain, or you are stitching PML, and things like that. So let's take a look at the pseudo assembly code on the right. So for the synchronous copies, I already told you that it's equivalent to loading and storing. Then we have branch jumps, loading and storing again, and loading and storing third time. So as you can see here, we get 3 stalls. In theory, compiler could have done better. It could have predicated 3 loads first, so send them all in flight, and then have predicated stores, but unfortunately, it does not do it, even for this particular example. So if we replace synchronous copies with asynchronous copies, it's not going to solve the branching and predication issue. However, asynchronous copies do not stall, so we'll observe only one single stall when we wait prior. Let's see what it results in practice. So this is essentially the same code. I only made one modification, that I made my thread block 2-dimensional, which is highlighted by red ellipses. And now my conditionals are actually on with respect to a slow axis, which means that I don't even have divergence within warps. So for H200, I observe a 1.3x speed up of this code over synchronous code. Moreover, if I do a 2-stage prefetching, which I'll explain later, my speed up goes up by a factor of 1.7, and the reported memory throughput is 84% compared to the original 46%. Now let's take a look at the NCU profiler here. As you saw in the pseudocode, we have 3 pairs of LDG STS, and each one has a lone scoreboard. In addition, we have another stall when we sync threads. And please pay attention to this scale number 20. So lone scoreboard takes more than 20 cycles. Stall barrier also is above 20. Now here's the asynchronous version. First of all, scale changed to 10, and you can see that lone scoreboard dropped from 25 to about 2. Also, stall barrier dropped from 23 to about 9, and now our biggest issue is Mayo throttle, which is due to a lot of LDS operations fired one after another, which overwhelms the MIO. Okay. So I already mentioned prefetching. Let me say a few words what it means. So when we do staging or prefetching, essentially we load data into shared memory for the next iteration while computing the current iteration. So it requires us to double the shared memory to have slice for the current and for the next iteration. Before we start the loop, we prime our copy with the first iteration data. And then right after we start the loop, at each iteration, we started with asynchronously copying data for the next iteration. So now, since we have 2 copies in flight, one for the current iteration, one for the next iteration, we want to wait prior one. At this point, data for the current iteration has arrived. We can compute, and then we proceed. Note that for the very last iteration, we don't need to prefetch anything. So last iteration so the count here is reduced by 1, and last iteration is done outside of the loop. You can throw away one of the sync threads here by introducing a 3rd layer of your shared memory, because in this case, when you have 3 layers, the next iteration cannot step onto the previous iteration, and one sync thread is sufficient. This is still a two-staged case because we only prefetch one next iteration. However, instead of prefetching one next iteration, you can prefetch multiple iterations, which turns our two-stage code into a multi-stage. I'm not showing the code here, but this is the definition of the multi-stage prefetching. Okay, here's a summary of how you can code LDG STS using various CUDA APIs. I used primitives in my examples above. You can also use libq++ API, or you can use cooperative groups. And here I show in blue comments how this C++ code maps into SAS instructions. In particular, note that for cooperative groups, it merges copy and commit operations into one. Okay, now I'll talk about synchronization. Before I talked about synchronizing LDG STS with the thread local synchronization. Now let's talk about synchronizing it with using a barrier, which is typical for producer-consumer case. So here I'm going to have a loop where at each iteration, some threads are producers. They fire asynchronous copy into shared memory. And then on completion, other threads that are consumers consume it, and it continues. So the code here starts with the barrier initialization. And note that expected arrival count is set to the number of producers. Then we have a loop. And first, let's take a look at the producer code. Producer fires copy. And here I have actually another loop because the amount of data that I want to copy may be different from number of producers. So this loop just covers the entire shared memory. On each iteration, the arrival barrier is reset with a number of the arrival count is reset with number of producers, and then this arrive, it attaches a barrier to the previous asynchronous copy, and since it's an arrive, it adds another number of producers. So the total number of arrivals can go up to twice number of producers. Then hardware will automatically decrement the count on completion, so it can go down back to n producers. And finally, second arrive gets the arrival count to 0, which will mean the phase flip. Note that this order is important here because otherwise you'll get plus n producers and then minus n producers, which is 0, so we have a premature phase flip. So from the consumer point of view, the code is pretty simple. You just wait on the phase flip, and then you use your loaded data. Okay, here I was going to talk about first Hopper copy from registers to distributed shared memory, but for the sake of time, I'm going to skip this now, and if time permits, I'll get back to this operation later at the end of my presentation. So let's go to first two TMA copies, which allow us to copy up to 5-dimensional block of memory, and we can fire this operation just by a single thread. So I already said that it's up to 5-dimensional. Can be fired by a single thread. Other features of this TMA, multi-dimensional TMA include filling out of bound successes with zeros or nones, and swizzling. And I'll describe it later in detail. So TMA copies come with some restrictions. In particular, shared memory address has to be 128 bytes aligned. Everything else has to be multiple of 16 bytes. And in order to copy 5-dimensional geometry, we introduced a so-called CUTENSA map descriptor, which can be passed as a kernel parameter or through constant memory. So let's talk about this descriptor now. So descriptor incorporates the following information. And all my pictures are going to be 2-dimensional, but it extends up to 5-dimensional. First, it's a number of dimensions of our tensor. Then base pointer, which is always attached to the top of the domain. Then tensor strides, which is this larger box, and tensor size. So strides can be bigger than the tensor. Finally, there is a box size which describes the size of the volume that we want to copy, and element strides, which I'll talk about later. So tensor descriptor cannot be changed inside kernels. For example, if you want to copy exactly the same geometry but from two different volumes in memory, you have to pass two tensor descriptors to your kernel that will have different base pointers. What can vary during kernel execution is the destination pointer, which is where the data lands in shared memory. In this case, I'm showing global to shared memory copies. And then coordinates, which tell it where this copy box is attached to our tensor box. So it can copy the same size copy box from any location inside the tensor. So I already mentioned that copy box does not have to be inside the tensor box, and if we are going out, the missing elements will be replaced either with zeros or nones. Now let's talk about element stride. So this picture is pretty self-explanatory. You can give strides to elements, and the copy will happen accordingly. Just note that the fastest dimension stride must be 1. Other strides are not supported. OK, now let's talk about the other direction. Copying from shared memory to global memory is pretty similar. There are a few differences. First, global to shared, you can copy either into local or remote shared memory. Shared to global, you can copy only from local shared memory. Synchronization is also, instead of barrier synchronization, it's done with a thread local synchronization. And finally, with respect to going out of bounds, you can go out of bounds on the right, but you cannot go out of bounds on the left. So coordinates must be always non-negative, which is kind of asymmetric. OK, so now let's discuss advantages of TMA copies over, for instance, LDG-STS. Here I'm showing the finite difference codes that typically compute derivatives from shared memory. And in this example, in order to load data into shared memory, we need to invoke LDG-STS on each of these 9 regions. Central region and then the halos. So for each region, we need to make sure that we don't run outside of the global computational domain, which is depicted by an X and Y here. On top of that, we need to compute different offsets into global memory and so on. So this entire code is replaced by a single TMA copy, which is unconditional with respect to domain bounds checks, and does not require any pointer arithmetics, which reduces register usage, predicate usage. We don't have any if statements, and MIO pressure. It can get even worse if the halos are wider than our thread block. Then in order to copy each green subdomain, you actually need to invoke multiple copies because they're not covered by a single thread block. And for TMA, it makes no difference. OK, it's important to know how TMA actually works. So all the copies are fired uniformly by a warp, which means that in a rare case, when you have a code where each thread fires a TMA code with thread-dependent parameters, the compiler will create this spilling loop over all these active threads within the warp. And within a loop, it will fire TMA instructions with the arguments of a particular thread. Typically, you just want to fire your TMA with a single thread. And in that case, you need to make sure you don't forget this if statement. Otherwise, you get multiple copies into the same destination, which is a data race. However, even though this code is correct, compiler does not know that the thread ID equals to 0 is true only for a single thread. So it will still create a pilling loop like this over active threads. Only one iteration of that, only a single iteration of this loop will be not a no-op. Other operations will do nothing. You can get rid of this pilling loop by using cooperative groups invoke one API as shown here. OK, so this is the summary of global to shared memory copies. First, we initialize a barrier. We synchronize in order for the initialization to be visible to everyone. Then we fire a copy, and we set the expected transaction count to the corresponding size that attaches a barrier to our copy. And finally, we wait on the barrier phase flip. The other direction is synchronized at a thread local level. So again, we fire a copy or several copies. Then we call a bulk commit group, which is similar to LDG STS. So we can have multiple batches. And then we wait for all batches except the last 10. So this is very, very similar to LDG STS. OK, now let's talk about another functionality of the TMA, swizzling. So I think I already mentioned swizzling, and here I'll basically repeat what she said. So TMA hardware can swizzle data while copying in order to avoid sharing memory conflicts. So let's take a look at this table that shows bank indices for shared memory two-dimensional array with 32 columns and size of T equals to 4. So the bank index is computed by taking the linear index in the array and taking a modulo 32. And this, if you can see, as you can see here, if a warp needs to access a column, which is typical, say, for matrix transpose, you end up with 32-way conflicts. So I think I already mentioned that one way to fix this problem is to add an extra column to the table, which basically tilts our bank ranks. And so you can see there are no conflicts both row-wise and column-wise. However, there is another way to swizzle, which is this formula to compute a linear index. And you can check the numbers. Again, there are no conflicts. So TMA can lend data in a swizzled way when you do a copy. And there are some restrictions. So first of all, the number of columns in your array times size of your type can be only one of three numbers, 32, 64, and 28. And TMA always operates on 16-byte chunks of data, so it swizzles 16-byte chunks within 128-byte segments. And here is basically a computation of swizzled index, but I just want to show you this table. It shows the swizzled column index of a 16-byte chunk. So, and this pattern repeats after 8 rows. OK, so finally, let me talk about, so far I've been talking about theory. Let me show you performance of the segmented sort for different kinds of shared memory. This test was provided by Allard Hendrickson, one of our dev techs. So you can see that for non-asynchronous copies, we achieve only 50% speed of light. And as we go to LDG STS, then essentially TMA without swizzle and TMA with swizzle, we achieve 87% speed of light. OK, now I'm going to talk about another set of operations. So these are one-dimensional TMA copies. One difference is that they allow not only copying between global and shared memory, but also between shared memory and local shared memory, or shared memory and remote shared memory. So basically, this operation is equivalent to a synchronous version of memcopy. It takes source and destination pointers and copy size. So there is no tensor descriptor, which means that you lose all the geometric functionality like swizzling, going out of bounds, and so on. Alignment requirements are slightly less strict. Your shared memory, instead of being aligned by 128 bytes, it only needs to be aligned by 16 bytes. And then synchronization is very similar to multidimensional TMA copies. You can either synchronize it with barriers or at a thread local level. OK, we are done with the longest topic, I believe. And now I'm going to switch gears again and talk about compressible memory. So compressible memory, it's a hardware-supported feature that allows to essentially compress data in global memory. So conceptually, what happens when data is being loaded from global memory, it is decompressed on arrival. And when stored to global memory, it is compressed before departure. So let's talk about some details. First of all, this feature is fully transparent. All you do, you change your allocation. So you replace your CUDA malloc with something else. Hardware takes care of the rest, and you have no control after that. It's important to know that compressible memory essentially compresses bandwidth, but it does not reduce your memory footprint. It works with 128 bytes granularity, and each cache line can be compressed either by a factor of 4, factor of 2, or it may not get compressed if the data is not nice enough. So this feature has been available since ADA, and now I'm going to talk about the main issue with the compressible memory. It can actually decrease your performance because it's very peculiar with respect to how you access memory due to special organization of compression cache. Okay, first let's look at several Saxby kernels. So this one is a simple one when we have one thread per element, and the number of waves in this case will depend on number of elements, as shown here. The second code is a so-called grid stride loop, in which each number of thread blocks is always fixed, and each thread steps with the grid size step. So the more thread blocks you have, the larger your step is, which means that you essentially decrease locality of your memory accesses. Another one is so-called block stride loop, in which case we first break our domains into a number of thread blocks, and then we iterate contiguously within a straight thread block, which means that if number of thread blocks grows, the locality gets improved. So now let's take a look at the performance results. So left table shows results for a smaller array, 1.3 gigabytes. Right table shows results for 13 gigabytes. As you can see in the non-compressed case, performance doesn't really depend much on which kernel you use. For the compressed case, the no-loop kernel behaves the best because it has the best locality. And as we expect for the grid loop kernel, and here I'm showing number of thread blocks, it's either equal to number of SMs twice or 20 times number of SMs. So I already mentioned that for grid loop, the locality gets worse, and we can observe it in the performance column of this table. For the block loop, locality gets better, and we can see that performance increases. If our array is 10 times bigger, then the tendency is the same. You can see that performance decreases here, increases here, but still there is not enough locality to beat the non-compressed case. So locality is crucial, and let me show. Okay, now this slide is about showing compression in NCU. So this is for 1.3 gigabyte test, and you can see that the reported ratio and reported amount of data that was written, they match the 1.3 gigabytes. And now let's talk about a slightly more complicated example. So this is a 3D finite difference kernel that simulates wave propagation. So the way these kernels are typically organized, since in famous paper by Polius, is that we break our domain into two-dimensional blocks. Each block corresponds to two fast coordinates. And we usually compute x and fast derivatives using shared memory with halos. And then we iterate along the slowest dimension, computing z derivatives using register queues. So what we do to increase locality here, we break the Z loop into smaller ones by introducing three-dimensional grid. So our thread block is still two-dimensional, but grid of thread blocks is three-dimensional. So why does it increase? Why does it improve locality? As you can see here, when one wave of thread blocks is finishing its Z loop, the other wave may be already starting. So you may have some threads operating on data at the very end of your volume, while other threads are operating on data at the very beginning of your volume, which means that your data accesses span the entire volume. Here, the situation gets proportionally better. instead of spending the entire volume, you spend only a size of your thread block along the z-axis. So let's see how it affects the performance. So here I'm showing performance for the 8th order TTI kernel, and don't pay attention to TTI. It's the particular physics that we use, and that requires 9 volumes of data. Given domain size 800 cubed, it's 2.2 gigabytes per volume. And this table shows performance on L40S card. So columns here correspond to different sizes of Z blocks. We start with no Z block and then go down to 32, to Z block size of 32. And this, as you can see, in case of no compression, there is not much effect on the performance. However, when we do compression, if our locality is good enough, we observe 3.5x performance improvement over the non-compressed memory. However, if there is not enough locality, actually our performance can go down by almost a factor of 10. Okay, now as we run more time steps of our simulation, the performance of non-compressed memory does not change, but performance of the compressed memory gets worse. And that's because the simulation starts with 0 pressure fields that propagate from the source location. So in the beginning, pressure fields are very compressible, obviously, and as they propagate, they become less and less compressible. Nonetheless, even after a very long simulation of 10,000 steps, which is pretty typical for production seismic runs, we still end up with overall 1.5x speed up on average. Okay, I already told you that there is no one-liner way to allocate compressible. There is no one-liner way to allocate compressible memory similar to CUDA malloc. Currently, you need to use virtual memory management provided by CUDA API, and here I'm showing the code. So main steps are: first, your allocation size has to be rounded up to the granularity. Then you reserve virtual address range, allocate physical memory, glue these two together, map your allocated memory to VA range, and then by default, the memory is not read-write accessible, so you need to set read-write access permissions. You can find all this information in the programming guide. Okay, now last topic of my tutorial is CUDA graphs. And this picture shows execution timeline when the kernels are short. Basically, since the CPU kernel launch latency is large, we observe gaps between GPU kernels. And CUDA graphs address this issue by creating a single graph object that requires only one launch, which can be heavier than each kernel launches, but then it is followed by GPU kernels that are tightly packed. So overall, we get a win. So here I'm showing a simple pattern where kernels B and C that they can run in concurrently, but they depend on the output of kernel A. So they need to be synchronized with respect to kernel A. Kernel D depends on the output of kernels B and C. So synchronization with respect to A and B and D is done by placing them in the same stream. However, in order to run kernel C concurrently with B and after kernel A, we need to use CUDA event record, CUDA stream await event API. So the simplest way to create a graph is just to capture, to do what's called stream capturing. So you surround your sequence of operations by CUDA stream begin capture, and then you finish it with CUDA stream end capture. So it basically creates an object that represents your workflow. And during capturing, actually nothing is run. It's essentially a dry run, so only the actions get recorded by a graph. So this is the first step. After you capture your graph, you need to do 2 more steps. You need to create an executable graph, and then you can finally launch it. And these 3 steps are kind of similar to writing a code. First, you write your code, then you compile your code, and finally, you execute your compiled code. Note that graph is launched with just 2 parameters, the graph itself and the stream. So despite being launched in the single stream, it preserves the recorded concurrency. Also, you can inherit stream priorities if you specify this flag. By default, they're not inherited. And since it is launched in a completely separate stream, you can destroy the streams that we used during capturing. So one issue we have here is that the graph launch just takes graph as an argument. So if you have kernel parameters, how do you change them? For example, this is a common time stepping pattern when we have a simulation with pointers to previous time step and next time step, and then we swap them for the next iteration. So here's what you can do. First approach, you can capture your graph at each iteration, which means you capture 0th and first iteration, and then you launch them in an alternate way. Another way is to capture your graph at each iteration, but instead of instantiating, which means compiling it at every time, you just update your compiled graph. And graph instantiation is a very expensive operation, whereas executable graph update is a much cheaper operation. Finally, there is an explicit graph construction API, which I'm not talking about here, but basically it gives you much more freedom. You can explicitly create a node, store a node handle to that node, and then you can alter node parameters while iteratively launching your graph. So the first approach, because we create a new graph for each set of parameters, it allows you to change topology. However, second and third approaches, they do not allow topology changes except for minor cases. For instance, you can turn a node on or off. Okay, so let's talk about some restrictions on graph capturing. First of all, you cannot use default legacy streams. So you need to, if you have it, you need to replace it with your streams. The rest essentially follow this instruction. Basically, you can capture only what you can put in a stream. So if you have synchronous mem copies or CUDA free, you need to replace them with asynchronous ones. Also, you cannot synchronize both stream level or device level. And if you want to capture some host logic, you need to also attach it to a stream. Okay, now let's talk about slightly more complicated kernel. This kernel is based on a seismic processing workflow. So we have a seismic trace, which is a single one-dimensional array. And we do some processing in the Fourier domain. So first we run a forward QFFT. Then we create multiple traces of different size by using frequency continuations. And then we have to do inverse FFT on each trace. But since each trace can have its own size, we cannot batch those. So we do this multiple inverse QFFTs in parallel. And after that, we do some processing. Say here, I run reduction on every even trace, and then I combine even and odd trace, and then I finally combine all the traces and I iterate. Okay, so that's the code, and I don't want you to understand it. I just want to note here that there is no extra effort to capture library calls. For instance, CUDA FFT call here or CAB library call here. It's all happens automatically. Okay, now let's take a look at the NCU profile. So in this example, which I ran on H200, my input trace has 1,024 samples. Then I have 100 intermediate traces that can be run simultaneously. And their sizes range from 128 to 8192. And for this case, I observe 5x speed up from using graphs. And here's the picture of the kernel launch timeline, and you can see how nicely packed and compact all the kernels are. Here's a picture when I do not use CUDA graphs. So what happens here essentially, because even though I use multiple streams, because each launch takes longer than it takes to run a kernel, essentially all those streams get serialized, and you accept this piece that happens after the long-running kernel. So you almost don't need to use multiple streams here. Okay, so in order to see that picture from the previous slide, you actually need to use this NCU option CUDA graph trace node, because by default, it does not trace inside the graphs, and if you run it on-site compute with default settings, you'll just see graph launches on your timeline, but you will not see the internals. Just note that when you trace inside the nodes, you can incur higher on-site compute overhead. Okay, so CUDA graph API is very rich, and I only talked about stream capturing. I just mentioned that there is a way to build graphs explicitly. There will be 2 more talks that talk about graphs at this GTC, which I highly recommend you to attend. One is by Jiri, and one by Chikun. And also here I list resources from the previous GTCs and technical blogs and some CUDA samples. Okay, it looks like I'm good on time, so I can, let me first give you a summary of what I talked about. So first I talked about memory model, and it's just, if you do parallel programming, it's pretty useful to know what memory model does, because it allows you to write correct and performant code. Then I talked about asynchronous memory copies and barriers. And the main benefits of those is increasing bytes in flight, plus less pressure, register, predicate, MIO. However, those require some programming effort. Then I talked about compressible memory, which can improve effective global memory bandwidth in case your data is compressible. And it can be a very low-hanging fruit, because all you need to do is to replace your CUDA mallocs with compressible allocations. However, there is a danger here, because we talked about sensitivity to access patterns, and compressible memory can actually slow down your kernels. So it may require kernel changes to be effective. And I finished with CUDA graphs, which is essentially a way to go for short-timed kernels. And again, it can be a low-hanging fruit, because stream capturing is just a few extra lines of code. However, if you want to have more detailed control, you need to use, say, explicit API, which is more complicated. And now, since I have time, I can get back to asynchronous copies, last kind of asynchronous copies, which is copying from registers to distributed shared memory. And it's essentially an asynchronous version of DSMem at some index equals your register variable. So it can be synchronized with a remote barrier. And here I'm showing C++ and corresponding SAS code. So let me show you an example. So we have a loop when we have 8 CTAs in a cluster. And each CTA sends data to the neighbor on the right. And it does it in a circular way. So last one sends data to the very first CTA. And this happens in the outer loop. So to implement this code, we need 2 barriers. One barrier notifies consumer CTA that data copy from producer is complete. And then if you want to go into next iteration, we need to notify, consumer needs to notify producer that it's ready to receive data for the next iteration to avoid overwriting. So let's take a look at the code. And here, non-important parts of the code are grayed out. So as I said, we need 2 barriers. One is called bar, another bar done, and shared memory. And first we initialize barriers. And you'll see later why I initialize barrier with a arrival count 1 and another barrier with arrival count equal to number of threads. Now, since we are dealing with the cluster level thing, we have to synchronize a cluster. Then this code in gray basically gives my local rank and rank of my left and right neighbor. And finally, before we go into iterations, we need to map shared memory from our neighbors. So since we going to copy to the right neighbor, we map shared memory from the next rank. For the barriers, because we are going to notify the right neighbor, we also map barrier from the right. But when it comes to notifying the producer, we actually are notifying the sender, who is on the left. So we map another barrier from the left. And I guess for you it's different. OK, so here's the code. First, we have our iteration loop. Then we have some ingrays. We set some data in a register. And then each CTA fires an asynchronous copy. And here you can see that I have a 1023 minus thread ID. That's just for fun. So as my data gets copied, it gets reversed. So you can have some other kind of permutation here. And then I attach this copy to the bar next, which is a barrier on the consumer side. And what this operation does, it decreases the arrival count by the size of my int4, which is 16, and it happens for each of 1024 threads on completion. So this is done automatically by hardware. Now, from the consumer point of view, I want to receive 16K of data. So I set my expected arrival count to 16K, which means that it will balance it back to 0. And it doesn't matter in which order I do these two operations, because phase will flip when I reach 0, so I can go one way first and then get back to 0. I can go the other way and get back to 0. So if you look at this code from the consumer point of view, I just wait on a phase flip. After that, I can access my shared memory. Now it's local shared memory data. And now I can notify the producer on the left that I'm ready to receive next batch of data. So I do barrier arrive, and this is done by every thread, whereas this is done by just one thread. That's why I have initialization with a 1 arrival count and 1024 arrival count here. So I notify the producer, and now if I am a producer, from the producer point of view, I wait on the bar done. And then because I do explicit phase tracking, I need to flip my phase. One thing to note here is you need to make sure that you use correct spaces when you call these functions. So barrier, it's a local barrier for the CTA. So I use space shared here. However, bar priv, it's actually, OK, here it is. It's a mapped barrier, so it lives in the remote memory. So I have to use space cluster here. If you screw this up, you'll end up with a very confusing kernel failure, which may be hard to debug. OK, so I'll finish my presentation with the list of other tutorials from the performance optimization track, and I'm ready for your questions.
Thank you, Igor. If you have a question, please go to the mic on the aisle or just raise your hand and I can come to you with my microphone.
Hi, I have a question about compressible memory. Why does it seem to be only available in the driver API?
Because the CUDA API team is lazy, I guess. I don't know.
Yeah, I mean, I would guess that, because if I just add the enum for that compressible memory in the runtime API, it just seems to work. So what's up with that?
I couldn't hear you well. Can you repeat the question?
No, I'm just saying, if I just add the enum into the runtime API, it just seems to work. So
what do you mean add enum?
The enum for the compressible memory.
Yeah, but it's not there currently. You have to use the
Yeah, but if I just add it to the header file, it seems to work.
Well, maybe we should discuss it offline because I'm not understanding what you mean.
OK, thank you.
I have a couple of questions. The first is, so is there a good way to know whether I'm using the swizzle size correctly? Or do I have to, or any guidelines that will help?
Well, basically, you'll use the swizzle size. You can look at it this way. So where is it? Oh. Basically, you know your number of columns and size of your T. That means that there's only one swizzle size that fits you.
Yeah.
So you need to choose that swizzle size.
Got it. Thank you. And one more thing is that, so LDGSTS, right? So it's very painful to change my application again with this pipeline and new sets of APIs that you just talked about. Isn't it, this is a point of view, isn't it better if the compiler takes care of it and then all the copies to the shared memory is by default asynchronous? Then I don't have to write and rewrite the application again and again.
Well, compiler doesn't know your intent. Maybe you don't want to. This is something that up to a programmer to decide. It would be, way too much optimization to make those decisions automatically, I think. So I don't think we intend to do that.
Okay. Yeah, and then last is, in slide 40, what's the unit?
40?
40. You talked about timing.
1 second.
I'm guessing it's milliseconds.
Oh, here it's, for this test, it's milliseconds.
Thanks.
I have another question about Swizzle.
Yep.
So I was curious if it outperforms the older approach of simply adding 1 to a dimension of our shared memory array.
Well, first of all, it saves you shared memory because you don't need extra column. Then it's done at the hardware level, so essentially it's no extra time compared to non-swizzled case. In the case of whether letting hardware do the swizzle for you or you do it manually, I don't know if there is much performance gain.
Gotcha. Thank you.
A question for compressible memory. What type of data are favorable in this case? If at all, could you share the algorithm for the compressibility?
No, the compressibility, it's not public information. What size? Well, it operates on 128 cache line sizes, basically. Your underlying type doesn't matter because it's essentially a C interface. It throws away the type information.
Okay, so I guess if I understand correctly, for deep learning tensors, they do not have very good compressibility in this case.
The compressibility will depend on your data. For instance, remember when I start with 0 wave fields, so they're obviously best compressible for X. Mm-hmm. If the data in your array is too random, so to speak, then it's not compressible. So, and as you write data, the same compressed volume may become more or less compressible. So you have random data, you write zeros there, your compression rate will go up to 4. You have zeros, you write random stuff there, you'll get no compression.
Got it. Thanks.
I can give some information about the compressibility. We don't disclose the algorithm, but you can think of if you have lots of zeros, those get compressed, and if you have lots of same bytes, it's going to get compressed also. So for zeros, for example, deep learning, if you have a tensor on which you apply a softmax, and typically you have about 50% of values that get to 0, all the negatives that could get compressed.
Similar to base delta compression?
It's like a scale, probably.
I'm not going to go further.
Oh, I have a question about synchronization of a cluster. So to be able to synchronize between SMs, so does it mean like all the blocks are scheduled, guaranteed to be scheduled at the same time?
So all the CTAs within a CJ, they're co-scheduled and they're guaranteed to run simultaneously. They may not start exactly at the same time. That's why you need to do synchronization before you access shared memory. But yes, they are co-scheduled. Otherwise, it wouldn't work.
So, but it will be definitely higher price when within blocks on the same SM or within one block. I mean, just kind of curious, like, for example, like something like what CUP implements with double, like with lookup, kind of a spin log to guarantee like blocks. So would it be faster to use the cluster in that case?
Well, it's faster to use the cluster if you can save global memory trips, essentially. So, because essentially, distributed shared memory increases your L1 size. That's what it looks like, right? So, if you can save trips to global memory, then typically it should be faster.
Okay, thank you.
Hello. Is there any possibility to actually limit what SMs are able to execute a kernel? The reason I'm asking this is because I've noticed that there are certain kernels that if I give them all the SMs, it actually performs slower than if I gave them a few amount of the SMs. And I think this is occurring because of the L2 cache to the SM. So is there any way to limit that programmatically in CUDA, or do we still have to do our old technique of just limiting, is it executing on this SM or not?
So you want to limit, can you explain again what you're trying to limit?
So what I've noticed is there are certain SMs that actually have a locality to the L2 cache. So you actually can read data from the L2 cache faster and write faster in those regions. However, the default techniques that I've noticed with CUDA, if I have a certain amount of blocks, it just wants to spread across every single possible SM. Some of those SMs are further away, and it has to go through the crossbar from the L2 cache to that. So is there any mechanism?
So you're asking about the stitch. Yeah,
Exactly.
there is no way to query, basically, if the current SM is on the left stitch or side of the stitch or on the right. It's not there is no API for that.
Okay, thank you.
With compressible memory, is the compression information associated with the virtual address range so that you can reuse the underlying physical memory for non-compressed cases?
I never thought of that. I don't know.
So I'm mainly concerned about like reusing the same buffer, and in some cases I might have use for compression. In other cases, it won't be compressed. So
yeah. We can talk offline. I don't know the answer.
okay, thank you.
The assembly you showed was really elegant for some of the asynchronous barriers, and also for the asynchronous copies. But when I've done the same thing, I've got a lot of extra overhead assembly. The main offender seems to be that the compiler doesn't know the thread block size at compile time.